Again, shape, center, spread, all of that is reviewed. And so as long as those conditions are met, the sampling distribution of the sample mean will look like this. It will be normally distributed approximately with mean mu, normal curve, mean mu, standard deviation, sigma divided by the square root of n. This can also be written purely in symbols. And so this means the same thing. X bar is distributed normally with mean mu and standard deviation sigma divided by the square root of n. This is equivalent to basically what this picture is telling you. Go ahead. All right. Next thing. So again, as long as the conditions are met, this is stuff we already know. This is review of Unit 5. We also know from Unit 6 that the basic structure of a confidence interval is the statistic plus or minus the critical value times the standard deviation. Where Z star is the critical value with the C percentage of the area lying between negative Z star and Z star. So as a reminder, that looks like this. So if you have a confidence level of 95%, that is going to be the middle percentage of your data here. And then this is going to be negative Z star, and this is going to be Z star. All right, and then you've got some tail probabilities out here, right? So the confidence interval for a population mean follows the same structure as the previous. So that would be point estimate. And you'll see the similarities throughout this unit, plus or minus the margin of error, right? Which is basically this part of the previous formula, margin of error. And so the point estimate for a sample mean is X bar, plus or minus the critical value Z star, times the standard deviation, which would be, in this case for means, sigma divided by the square root of n. And so notice the structure is really, really similar. It's just the standard deviation and the point estimate take on kind of a different thing because we're talking about means and we're not talking about proportions anymore. So when you're doing a CI for a mean, you either know the population standard deviation sigma or you do not. Okay. And so we're going to examine the known sigma first, which is so rare. Like it's so rare that happens, but we start here because it's familiar to us. So this farmer wants to estimate the mean weight in grams of all tomatoes grown on his farm. And to do this, he's going to select 4 tomatoes, calculate the mean weight in grams. He calculates that to be 110 grams. And we assume that the population of his tomatoes, their weight is normally distributed. So we're going to use the sample mean to create a 99% CI for the population mean. Notice in bold, it says, just suppose the standard deviation of that population is 40 grams based off of previous information. So this is a 4-step process, just like it always has been. And so we're going to state first. And the state step, I like to do a little more when I'm working with means. I just make sure that I've got all of my stuff really clearly ready to go. So first thing we're going to do is we're going to define the population parameter, which in this case is no longer P, it is mu, the true, bless you, mean weight of all his tomatoes, right? And there are some things I'm going to need in order to calculate this confidence interval. So we're going to make sure that we mention that this is a 99% confidence interval. And that's going to give me a Z star. I'm going to have to calculate that. Remember, kind of as a side note, you do not have to show what I'm about to show, but I want you to remember how to do, get the Z star. That's inverse normal. And then the area would be 0.01 divided by 2. What's the other thing it asked for? I don't remember. Mean and standard deviation. So What's the mean? So you're going to calculate your Z star. You should get 2.576. We're not going to use the 110 though. Why not? 0 and 1. Why? No, we're doing a Z score, right? So mean 0, sigma 1. And that's going to give us the appropriate critical value. All right. So I'm going to also need a point estimate. X bar is 110 grams. And it gives us sigma, the standard deviation. And that's going to be 40. I also have a sample size of 4. All right, so I'm just kind of organizing all of my work here. Because next I'm going to do the planning step. All right, so when we plan, we're going to name the procedure. I have one sample, so this is a one sample. Z, I'm doing an interval, not a test, so this is an interval. And not for P, but for mu now, because that is the new population parameter. This is going to be a one sample Z interval for mu. And we're going to check some conditions. The conditions are the same. Okay, so when we go to do that, we'll check the random condition. And that was stated in the problem. You can quote it, you can say it was stated, it's easy to go back and see that. We want to check independence. We are sampling from a finite population without replacement. So that means that 4, our sample size must be less than or equal to 10% of all his tomatoes. We assume that would definitely be true, right? Definitely got more than 40 tomatoes. And then normal. How do we know that the sampling distribution will be normal here? What it says what exactly? Right, it says the population is normal. So population, you have to explicitly make that connection. Population is normal. You have to show that you know why the sampling distribution will be normal. So the population is normal, so the sampling distribution will be approximately normal. It's not sufficient for us to, like, normally we would check n times p, n times 1 minus p, and that would be your evidence. Here you'll just write that you understand that the normality is inherited from the normal population that we're sampling from is approximately normal. Okay, so now that we've checked all our conditions, we've named our procedure, now we're ready to actually do something. All right, so let's do, and the general formula that we're looking at here, I'm trying to construct a confidence interval, so this is going to be point estimate. Plus or minus the margin of error. Specific formula, X bar plus Z star times sigma divided by the square root of n. And then we'll just start plugging in those things that we've already done. 110 plus or minus, our Z star was 2.576. Population standard deviation 40 divided by sample size square root of 4. And so that's going to give me an interval of 58.48 to 161.52. And now we're ready to write our conclusion. There will be no new interpretation sentences, I don't think, until Unit 9. We're just going to be reusing the ones we've used so far. So we are 99% confident that the interval from 58.48 grams to 161.52 grams captures the true mean weight of all his tomatoes. All right, so one distinction here that we need to make sure we add when we're working with means that does not have to do with proportions. Proportions don't have units. They are just a part to whole kind of ratio relationship. But these do, right? And so that's a really easy way to go from a 3 to a 4 to a 3 on FRQ is to not tell me what those numbers mean in context. We're talking about grams. We're not talking about pounds. We're not talking about tons. We're not talking about milligrams, but we want to make sure that we include the units. So again, to restate what we stated earlier, what we just created is called a one sample. One sample. Just in a second, it'll write for me. Sample Z interval for mu. And there's a reason that I restate that over again, okay? So the basic gist of this entire block of text that's there really for your reference is when we made this interval, we assumed that we knew the population standard deviation, which is absurd, right? Because like if we're making a confidence interval, we're never going to know that because we don't know the population mean. We're not going to know those things about the population. That is not reasonable, okay? When we do not know it, we have to take the best estimate for it, and that is the sample standard deviation. Okay, but we know that a sample has so much more variability than repeated samples over and over and over and over and over again. So we have to account for the fact that we are making a rough estimate. And so in order to do that, when we make that substitution with the sample standard deviation instead of the population, we have to adopt a new test statistic. Z is no longer valid. We have to use now the T statistic. It has a new distribution that is associated with it. It is not normal except in one specific case. And we'll talk about that for the next few minutes. So the new statistic is now called the T statistic. It has a new distribution, and the new distribution, which is called the T distribution, not the normal distribution, but the T distribution, or it's also called the student T, or the student's T distribution, for the guy that discovered it. He wrote under a pen name because the Guinness Brewery didn't want their name associated with all of this work. So they just called him the student. So the student's T distribution is not exactly like the normal curve, but it is very close to it. So notice in the picture, you have your standard normal, which are your z-scores, and then below it, similar in shape, but flattened and stretched out and a little more fat in the tails, is the T distribution. So it is still centered at 0. It is still bell-shaped. But its spread is slightly greater than the standard normal. Okay? Notice the variability is a little bit more because there's more going on out here on the edges. It has more area in the tails. The area still sums to 1, but it's just a little bit different. It's a little flattened out. So, the special thing about the T distribution is it is not a single curve. It is a family of distributions. And its different kind of forms it takes on are associated with specific sample sizes. So for every sample size, there is a different T curve. It slowly adjusts and approaches being exactly the standard normal as the sample size approaches infinity. So as we approach larger and larger sample sizes, we get closer and closer and closer and closer to the standard normal. So the way we determine which curve we're going to use is by something called the degrees of freedom, abbreviated DF, and calculated by subtracting 1 from the sample size. Okay. So you're not going to have these standard memorizable T's like we do for Z's, right? We have certain Z's that we use a lot. They're the exact same every time you use them. This one is going to be contingent on the sample size and the confidence level. So it's a little more complicated. So again, the tails on the T distribution are fatter than the standard normal. And again, it's because sample size is large, smaller sample sizes, the more variability we have, hence the fatter tail. So if you look down here, you see the green, really flat DF of 4. As DF goes up to 30, our sample size is getting larger. We're more closely approximating the normal. And then the standard normal is DF infinity. So from there are 2 ways to find the probabilities, areas, etc., under a T density curve. You can use table B, which I gave you today, or you can use the inverse T function in the calculator, which is different than the inverse normal. Okay, so the way to find the inverse T function in your calculator, and let's all make sure we can do that because I don't think anybody likes the table. This is second bars inverse T, which is number 4. Okay. So what we're actually trying to do is, if you look at this table, I'm going to show you the table first, and then I'm going to show you the calculator. The table shows you the tail probabilities and the degrees of freedom. Okay. So if I am looking to calculate a 90% confidence interval for n equals 30 to get T star, this is kind of what I need to think about. So if I have the curve, I'm going to have 90% here. So how much in each tail? 5%. I'm going to split the remaining 10% equally. This should be kind of a review, right? So this is the tail probability. Okay. So what I'm going to do is I'm going to go over and I'm going to find that tail probability here. You see it? Okay, so I'm going to use this column. Then I'm going to go over to the left-hand side and I'm going to find the matching degrees of freedom. So if n is 30, the degrees of freedom would be what? 29. So I'm going to go find 29 over here. And then wherever that intersects is the appropriate T star for this particular situation. So using the table, T star equals 1.699. Okay. So we're going to find tail probability column and DF row to get T star critical value. That's how you use the table. Okay. This is method 1. Right, method number 2 is the one that I prefer because I hate these stupid tables. If you love them, then that is perfectly fine. That's just a difference in the way people's brains work, and that's cool. I prefer the calculator. So I'm going to use the inverse T, and it only wants 2 things. The area, which it's referring to the tail probability or the tail area, and the degrees of freedom. So when you plug that in, make sure you can do that. You will get a T star of exactly the same thing. And this is just, this 90% is just your confidence percentage, right? Your confidence level. Can everybody find that inverse T command on your calculator? We got it? Okay. This will be important. You're going to be using what we call T procedures a whole lot moving forward. And so being able to calculate those specific T stars is really important. All right, so that is finding T star. Let's do a couple more. So real quick, we're going to do these two examples. So for a 95% confidence interval, what is the tail probability? Yeah. So it's just 5% divided by 2. So that would be 2.5%, which would be 0.025. And what are the degrees of freedom for n equals 25? 24. For the 96% confidence interval, the tail probability would be 2%, because we're going to take the remaining 4% under the curve and equally distribute it over the two tails, which would give me 0.02. And the degrees of freedom for 230 would be what? 229. So you'll notice in this one right here that your table B goes in increments of 1 all the way up to 30, and then it starts skipping, right? So for this one, because you have the exact degrees of freedom, you're going to get the same T star from both the table and the calculator, okay? And that's going to be 2.064. And I'll write it again just to illustrate later in the notes. So from the table B, you get this. From the calculator, you get the same exact thing. Now, let's take a look at table B. Is there a degrees of freedom 229? What's the highest it goes to? Does it go to? Does it go to? Okay, so it goes. So it jumps from 100 to 1,000. So if you had to go to the closest one, what would you go to? Yeah, so here I'm going to have to round down to DF equals 100 and pull that T star. And so what that's going to look like is from the table, you're going to get 2.081. Now from the calculator, you'll be able to use the exact degrees of freedom and you'll obtain 2.066. Both, you'll be able to answer any question on the AP exam using either. But as you can see, your answers will be slightly different. Okay, so it's important that if you're using table B, you recognize that you're not going to be able to get an exact probability or critical value. Okay, just so you know. All right, so this is calculating the appropriate T stars. All right, so now constructing a confidence interval for a population mean when you do not know the population standard deviation, which obviously we will not, right? Except in AP Stats class where they ask you some random conceptual question. So the conditions are pretty much exactly the same when you do not know sigma. Random assignment is when we are doing experiments. We can establish randomness and that required condition with random assignment or random selection if you're sampling. Either one is sufficient, but you have to have one of them. Normality, if the sample size, this is new, if the sample size is less than 30, you have to make sure that the sample you're looking at is normally distributed. You will either have to graph the data or it will be stated in the problem. So if that happens, you're going to have to say, you're going to have to give me a box plot, a histogram, etc., to visually provide evidence that your sample is normally distributed. We can only do this when using the T test statistic. It is resistant to low sample sizes. Okay, as long as your sample data is normal and you're using the t statistic, it's cool that you just look at the sample and be like, it's good enough, right? So it's very, very like what we call robust. It can handle weird stuff going on and still give accurate inferences. So the sample size is greater than 30, then, we don't care because the CLT says it's cool, all right? Then condition number 3 is the same as it's always been. Independence: when you are sampling without replacement from a finite population, the sample size N must be less than 10% of the population size, which you have seen this over and over and over and over and over, right? All right, so once you have established those well-known conditions, you can use the following procedures with the T and the Z statistics. So the one sample T interval for means looks like this: X bar plus or minus T star times the sample standard deviation, S sub X, divided by the square root of N. The one sample Z interval for means is X bar plus or minus Z star times sigma divided by the square root of N. The Z interval is used when the population standard deviation sigma is known, which is extremely rare. Okay. And the T interval is used when we do not know sigma, and therefore we are using our best estimate, which is S sub X, or the sample standard deviation. Okay, so you'll have to know which is the appropriate interval to use. Z is always preferable because it's more perfect. It gives us more information about the population. So if we can use Z, we want to. But if we have to make that substitution, remember there were times where I was like, hey, we don't know any better, so we got to use PI instead of P. This is another situation where, we don't know sigma, we have to use S sub X. Okay. All right. Let's do one together. You're going to do some of this as I do it, because some of it's going to be like reviewy. Some of it's going to be like making sure we can use the calculator and we know what to do. But I'm going to walk through the 4-step process with you. And the rest of the time is going to be you doing some multiple choice and free response to get ready for your quiz tomorrow. Okay. So a recent New York Times article reported that if you average 300 minutes a week of moderate exercise, you would be able to ward off cancer. That's a claim. For a working adult, that's a lot of time. So you set out to determine what the average amount of exercise time adults get in a week. You take a random sample of 10 U.S. adults who exercise and ask what their exercise time is per week. And this is the data that was obtained in minutes per week. Construct a 95% confidence interval to estimate the true population mean. So we're going to start out with our state step. Notice the difference here is that you don't have any statistics. You're given the raw data. Okay, so you're going to have to do some stuff. So the first thing we're going to do, as always, is we are going to define the parameter of interest, which is mu, the true average or the true mean, the true average time per week spent exercising by U.S. adults who exercise. All right. So just like before, there's some other stuff that I want to make sure that I've kind of got down. The sample size is 10. I'm going to need an X bar. I'm going to need an S sub X. I'm going to need some degrees of freedom because I'll be using the T procedures. And I'm going to need a T star. I'm just kind of getting ready here, right? There are several things that I need. We can do the degrees of freedom right off the jump. What are the degrees of freedom? 9. All right. Now that we've got degrees of freedom, I can calculate the T star. I'm looking at a 95% confidence level. And so the T star is going to be given by, let's see, inverse T. The area is going to be 0.025, and the DF is going to be 9. I always keep that to 3 decimal places and make sure you can get 2.262 for that. Now, how are we going to get X bar and SX? You can, like, your first instinct is going to be to like add them all up and divide by 10, but how are you going to get that standard deviation? The best way to do this is using the list in the calculator. Punch all the numbers in, make sure they're correct. You want to punch them in, then do another pass to make sure that you didn't flub it. And then you can do the single variable statistics, and it's going to give you SX and X bar. So you don't have to do that super long calculation of the standard deviation. So we'll skip straight to that. It's easy to make an error when you're entering a list of data like this. So that's why I say punch it in and then go back and double check it again. Because you flub your mean here and it's going to be like potentially pretty catastrophic as you move through the problem. And then again, it's the single variable statistics. Something that's really important here, you don't need a frequency list. These are not probabilities. Remember, we were doing expected value and the mean of a probability distribution. You had that frequency list. So I want everybody to make sure you know how to remove the frequency list option. Make sure we can all get the same thing here. So I'm going to put the mean that I get up and make sure you get the same thing. Should be 283.2. And SX is just literally SX in there. 2.04. Be very careful that you don't pull. Notice the difference between SX and sigma X in the calculator. The population standard deviation is way lower than the sample SX. Everybody good? If you can't find it or if you're getting something different, tell me so I can help you.
I got a few numbers off.
Okay.
I got the same.
So you got that frequency list in there? You have to remove the frequency list. Okay, there you go. So just clear that out. The only time we're going to use that frequency list is when you're doing the probability distribution mean, because we want to weight those. But we don't want to weight anything here. We want each of those data points to show up exactly one time. What is it? Stop. Edit. Welcome. And then go to single variable statistics. Calc. Notice you have a frequency list. You need to clear that. Be clear. There. There we go. All right, so now that you have this kind of like you're set up and ready to go, now we can begin the plan. Hopefully now you see with finally having a change with the name of the procedure that how those kind of work. This is a one sample T interval. Our test statistic is no longer Z, it is now T. And our parameter is no longer P, it's now mu. So this is a one sample T interval for mu. And then we're going to check some conditions, and this is going to take longer than normal. So the first one is random. It says random sample of 10 adults in the problem. Of 10 US adults or whatever, right? Literally says it in the problem. Independent. Since we are sampling without replacement from a finite population, we have to check that the sample size 10 is less than 10% of all US adults, our population. So that's good. And then we need to check for the normality of the sampling distribution. Well, the two ways that we learned about in Unit 5 that we could do that is inherit that normality from a normally distributed population, which it does not say. It does not say that this population is normally distributed. Or to have a sample size that meets or exceeds 30. Our sample size is 10. So notice how neither of those methods is going to work, right? But because you're using what we call a T procedure, or the T statistic is in play here, we're going to graph the data, graph the sample data. I'm going to make a box plot. So all the way back to Unit 1, where this would be 240, this would be 250, 260, 270. Hundred, 10, 20. You will literally have to construct this from the data and draw it on the paper. Remember, you have to label the axis. This is minutes per week. And then remember, we use the minimum, which you can obtain from your single variable statistics, the minimum. Q1, which is also in your single variable stats, the median, which is also in your single variable stats, the Q3, which is also in your single variable stats, and then the maximum. Okay, so we're going to construct a box plot and see if there is any obvious skewness or outliers, which is there. Does it appear to be roughly symmetric? Yeah, roughly symmetric. So, but we have to talk about that, right? So the data has no strong skewness. Or outliers. So we will continue. Assuming the sampling distribution will be approximately normal. So you can make a histogram if you want. Dot plot, the box plot is going to show the skewness and the outliers the easiest. Okay, so I usually prefer the box plot because it's the fastest. Okay, after we have named the procedure, check the conditions, we can proceed to actually do something. Right, and our general formula will be that for the confidence interval. So this is going to be the point estimate plus or minus the margin of error. In specific for means, that's going to be X bar plus T star. We're using the sample standard deviation since sigma is not known in this case. So S sub X. But lucky us, we already wrote all those numbers down, so it's just a matter of plugging them in now. So the X bar would be 283.2 plus or minus the T star, 2.262. S sub x, which is 22.04, divided by the square root of n, the sample size, which is 10. Which is going to give us an interval of 267.43 to 298.97 roughly. All right. And now we can finally write our conclusion sentence, which is the same old run-of-the-mill conclusion sentence that we have been writing for a confidence interval for a super long time now. We are 95% confident that the interval from 267.43 minutes to 298.97 minutes captures the true average time U.S. adults spend exercising per week. So that is the construction of the interval, but then it asks us an additional question to evaluate a claim. If you go back up, it says, based on this confidence interval, do you believe that we are exercising enough to ward off cancer? So if you go back up here, that's this question right here. And what's the number that says we're warding it off? So the claim is that if you average 300 minutes a week of moderate exercise, you could ward off cancer. So based on the interval that we see here, what do we believe that U.S. adults are exercising a sufficient amount? Why not? Right, 300 is not in the interval, so it's not a feasible value based on what we have done. So we'll say because this interval does not contain 300 minutes. We do not believe that the average adult is exercising enough to ward off cancer. Alrighty. Notice one thing real quick, a distinction I want to make for you is it doesn't